All right, let's dive right in. At the absolute heart of radiotherapy, there's this incredibly powerful, totally natural process called nuclear transformation. Today, we're going to unpack the physics of how unstable atoms change, and believe me, if you're getting into medical physics, this is a concept you've absolutely got to understand. Our whole story really starts with this one foundational experiment. So just picture a little chunk of radium, and it's shooting out these invisible rays. But then, when you stick it in a magnetic field, something really amazing happens. The rays split up into 3 different beams. I mean, that simple observation just begs the question, what in the world are these 3 things, and why do they act so differently? This discovery literally cracked open the secrets of the atom's core. So, to figure that out, here's our game plan. We'll start with the basics. What even is radioactivity? Then we'll see how something that seems totally random is actually super predictable. We'll get into its master clock, the half-life, trace a few radioactive family trees, and then, this is the best part, we'll see how all this theory is put to work saving lives in a hospital. Okay, so let's start at square one. What exactly is this natural phenomenon that Henry Becquerel just stumbled upon way back in 1896? What is going on deep inside an atom that makes it radioactive in the first place? Well, at its core, radioactivity is just a nucleus on a quest for stability. You can think of an unstable atom as being way too energetic, kind of jittery. And to calm down, it has to throw off that extra energy, either as a particle or as a wave. It's a totally natural, spontaneous way for it to just chill out and get to a more stable state. And this brings us right back to that first picture, because this shows the 3 main ways a nucleus can do that. You've got the heavy, positively charged alpha particle, it only bends a little. Then there's the much lighter, negatively charged beta particle, it gets yanked way off course. And finally, the gamma ray. It's pure energy, no charge at all, so it just sails straight through, completely unfazed. Now here's a really cool paradox. If you take any single atom, its decay is a completely random event. There's no way to know when that one specific nucleus is going to transform. So how on earth can we use something so chaotic for anything practical? Well, the answer is all about statistics. It's kind of like flipping a million coins at once. You can't possibly predict any single coin flip, but you can be almost certain that you're going to get about 500,000 heads. It's the same exact idea with atoms. When you have a huge group of them, their collective behavior becomes incredibly predictable. And here's the real key. The rate of decay, how many atoms are transforming every second, is directly proportional to how many radioactive atoms you have to begin with. The more you have, the faster they decay. And the link between those 2 things is a very special number we call the decay constant, or lambda. Every single radioactive element has its own unique lambda that defines how fast it decays. Now, this rate of decay has its own special name. We call it activity. Just think of it as a way of measuring how hot a sample is right this second. We measured in a unit called the becquerel, where 1 becquerel is just 1 atom falling apart per second. Now, in hospitals, you'll also see an older unit, the curie, which is it's a much, much bigger number. And the beauty of this is that it's all captured in one elegant, incredibly powerful formula, the exponential decay law. With this one tool, if you know what activity you started with, and you know that special decay constant, lambda, you can predict the activity of that sample at any point in the future. This thing is the absolute bedrock of all the calculations we do in radiotherapy. Okay, so that decay constant, lambda, is essential for the math, for sure. But there's a much more intuitive way for us to get a feel for the speed of decay, and that's the half-life. Let's take a look at this sort of radioactive master clock. The half-life is, it's exactly what it sounds like. It's the amount of time it takes for half of your radioactive stuff to decay away. So after 1 half-life, you have half of it left. If you wait for another half-life, you have half of that left, so a quarter of what you started with. After a third, you're down to an eighth, and on and on. It's a really simple, really elegant rule. And here's how it all connects. The half-life isn't some totally separate concept. It's directly tied to that decay constant lambda. They're really just 2 different ways of describing the exact same physical property. If you know one, you can always find the other using this super simple formula. Now, check this out because this is a really neat trick physicists use to visualize decay. If you plot it normally, like on the left, you get that classic steep curve. But we prefer the graph on the right, which is a semi-log plot. And why is that? Well, because it magically turns that curve into a perfectly straight line. And that makes it unbelievably easy to read the data and accurately predict what the activity will be way into the future. So the story actually gets even bigger than this. See, radioactive atoms don't usually just decay once and then call it a day. A lot of the heaviest elements go through a really long chain of transformations, almost like a multi-generational family tree. Out there in nature, there are three of these great radioactive families: the uranium, actinium, and thorium series. Each one starts with a really long-lived ancestor, and then it cascades down through a series of children and grandchildren, spitting out alpha and beta particles along the way, until they all finally find peace at the end of the line as a nice, stable, non-radioactive atom of lead. And this chart is a perfect illustration of one of those journeys. This is the uranium series, kicking off with uranium-238. You can literally trace its path as it decays, step by step, passing through some famous descendants like radium-226 and radon-222. You might actually know that one as a source of background radiation in people's basements, before it finally ends its long journey as stable lead-206. Now, something really fascinating can happen in these decay chains. If the parent element has a much, much longer half-life than its daughter, they can reach a kind of balance. Imagine the parent is slowly creating the daughter, but the daughter is decaying really fast. Eventually, you get to a point where the rate of creation perfectly equals the rate of decay. We call this radioactive equilibrium, and it's awesome because it creates a steady, predictable source of the daughter's radiation, all governed by the parent's much slower clock. Okay, so that's a lot of theory. You might be asking, why does any of this matter? Well, it matters because in medical physics, these exact principles are being used every single day to treat patients. This is where the physics becomes medicine. All right, let's put on our medical physicist hats for a minute and tackle a real-world problem. A hospital is using a powerful cobalt-60 source for radiation therapy. Now, they absolutely have to know its precise strength to give the patient the correct dose. So, we know its half-life. How much of its initial 5,000 curies of activity is going to be left after 4 years? Okay, step one, we know the half-life of cobalt-60. We can just look that up. But our big decay formula needs lambda, the decay constant. So the first thing we've got to do is use our little conversion formula to turn the half-life into the decay constant. This just gets the number into the right format for our main equation. And now for the final step. We have all of the pieces of the puzzle. We just take that decay constant we calculated, plug it into our exponential decay law along with our starting activity and the time that's passed, and we just let the math do its thing. And there we have it. 2,952 curies. But here's the really important part. This isn't just a number in a math problem. This precise calculation is what allows a medical physicist to adjust the treatment time every single day, making sure the patient gets the exact prescribed dose of radiation, even as the source gets a little bit weaker over time. It is a direct line from nuclear physics to patient safety. So we spent this whole time talking about how unstable atoms release energy all on their own, naturally just following their own predictable clocks. But in radiotherapy, a lot of the time, we need to create radiation exactly when and where we want it. We need to be able to turn it on and off. And that leaves us with a huge question for our next chapter. How can we actually generate useful radiation, like X-rays, on command?